Dr. James Lovelock, a NASA scientist, environmentalist and futurist, hypothesised that the Earth is like a single giant organism whose living and non-living components form complex interacting systems that regulate the condition of the planet. This is known as Gaia Theory, and these complex Earth systems determine the state of our environment, which has remained largely stable throughout human history and has allowed our society and economy to develop. However, these systems are changing now more than ever, so we need methods of monitoring them to allow us to make better decisions about how we manage our environment. The only continuous and reliable way of doing this over large areas is by using satellites. This is known as satellite remote sensing. In this video, we're going to explain how satellite remote sensing works and why it is so important for sustainable development and tackling climate change. But just before we get into it, we'd like to apologise for not being very active the last few months. Two of our members were very busy finishing their PhDs, but since they have finished, we've been working really hard to research and edit a cracking lineup of videos. So make sure you subscribe and hit the bell icon to stay up to date. We also have some really exciting news regarding the next major step in developing OurEden, so watch until the end to find out what it is. Broadly speaking, remote sensing is the process of gathering information about something without coming into contact with it. For example, taking a photograph with your smartphone. Satellite remote sensing has become increasingly important for mapping, monitoring and understanding the Earth's natural systems in near real time at both local and global scales. It is an extremely powerful tool for assessing information across large geographic areas like entire forests, continents or oceans, where frequent ground-based measurements would be too expensive or time-consuming. This allows scientists to create data sets that can inform environmental decisions and government policy. There are two main types of satellite remote sensing: passive and active. Passive remote sensing measures the radiation that is reflected or emitted by the planet, whereas active sensors emit their own radiation and measure its reflection. For passive sensors, typically the data we are most interested in is emitted thermal infrared radiation and reflected sunlight. Infrared allows us to measure the temperature of the land, sea and atmosphere, and visible wavelength data allows us to see the surface in real colour. But we can also use these measurements to determine a lot of other useful physical parameters, such as the amount of vegetation, water vapour, soil moisture, and many more. This data is used for a variety of environmental applications, which include monitoring air quality, detecting flood or drought risk, tracking ocean plastics, and deforestation. All these applications are satisfied by monitoring only a few global Earth systems. A common example of active remote sensing would be synthetic aperture radar, which is a complex technique that utilises radar to detect movements down to a few millimetres from space. We can use this to monitor things like infrastructure integrity, oil spills, deforestation and urban growth. To better explain how this data is gathered and processed, we'll briefly discuss two classes of satellite orbits and how they relate to Earth observation, that being polar satellites and geosynchronous satellites. Most Earth observation satellites are in a low Earth orbit at an altitude of less than 1,000 kilometres, or 620 miles. This is just above the atmosphere, which would cause drag, and below the inner Van Allen belt, which is a high radiation environment that could damage the spacecraft. These satellites are usually in polar orbits, meaning that they travel between the poles while the Earth rotates below. Completing one orbit takes around 2 hours, and the satellite continuously acquires images of the Earth along its ground track, known as a swath, which can be stitched together into one continuous image. The swath will eventually cover every inch of the Earth, providing global coverage. The width of the swath determines how long it will take to cover the globe, and this depends on the resolution of the instruments on board. These instruments are designed to measure particular frequency bands. For example, the Terra Satellites MODIS instrument measures 36 different bands of light, including visible light, as well as many different infrared bands. It has a swath over 2,000 kilometers wide with resolutions of 250 meters to 1,000 meters per pixel. With this swath width, the MODIS satellite generates a new image of the Earth almost every day. Each band provides unique information, and combinations of bands can be used for calculating things like pasture conditions or cloud properties, and of course generating colour images. This data is incredibly useful for monitoring things like flooding, phytoplankton blooms, wildfires, and deforestation. Geostationary and geosynchronous satellites are very different from polar satellites. They orbit much further away at about 36,000 kilometers, and this distance is deliberately chosen so that the satellite orbits the Earth at the same rate the Earth rotates. This means that geostationary satellites are always directly above the same spot on Earth. It also means that their ground receivers can stay fixed, pointing at the satellite's position in the sky, much like how a TV satellite dish works. The disadvantage is that it will never see the other side of the planet. A good example is Meteosat 10, which sits directly above Africa and Europe and captures data every 15 minutes. The two main instruments on Meteosat are Severi and GERB. Severi is a meteorological instrument used to monitor things like temperature and clouds. This is very useful for forecasting the weather in Europe and Africa. GERB, on the other hand, measures how much of the sun's radiation is reflected and absorbed by the Earth. This is very important for climate studies, as the more radiation is absorbed by the Earth's surface, the more the Earth's oceans and atmosphere will heat up. Over the years, instruments like these have made some crucial discoveries in climate science, like how important polar ice is for reflecting away excess solar radiation. So there are several satellites orbiting the Earth constantly acquiring data, but how is that swath data converted into images we can use? Well, the simple answer is a lot of image processing. Firstly, if we want images showing the Earth's surface, we have to take them when there are no clouds, and this may require many satellite passes over the same location before enough cloudless data is gathered. Secondly, the swath data from different satellite passes need to be stitched together to form a mosaic of the area of interest. Wide swath instruments cover a large area, so we can generate cloudless images very quickly, typically in about 1 week. But higher resolution instruments have narrower swaths, so getting complete high resolution mosaics of the Earth's surface can take up to a month. Carbon Brief has an interactive infographic which shows different satellites and what they are used for. The Earth's climate is changing in many ways that will affect our lives, so we need to maintain ways of understanding how and why these changes are occurring and how we can adapt to them. Satellite remote sensing is a technique for gathering this data, and it does so frequently, continuously, and over large areas. However, simply gathering data doesn't stop climate change. To do that, we need targeted and effective action, and that's where the data comes in. Governments and organisations can use remotely sensed data to make more informed decisions and develop more effective plans for environmental action on a national or international level. They can also use remote sensing to measure the impact of their policies. This is because satellite remote sensing has been identified as a vital technique for monitoring our progress towards the Sustainable Development Goals. The SDGs, established by the UN in 2015, comprise 17 goals and 169 targets, which have been adopted by world leaders as universal calls to action to end poverty, protect the planet, and ensure that all people enjoy peace and prosperity by 2030. This agenda stressed the importance of satellite Earth observation data in informing the targets and monitoring their progress. This is spurring rapid growth in the remote sensing industry. From 2007 to 2016, there were 181 non-meteorological Earth observation satellites launched, and by 2026, it's estimated that we will have over 600 large Earth observation satellites, and countless small ones, monitoring and evaluating the environment. Click the link in the description to find out more about the SDGs and let us know if you'd like us to make a video about them. But wait, we have an exciting announcement to make. The OurEden team has recently gained a new member who can speak Spanish, so we've just launched a Spanish channel called Nuestro Eden. Our new member is currently in the process of translating our videos, so if you prefer to watch our content in Spanish or know anyone who would, please head over to the channel and subscribe. If you'd like to know more about remote sensing and how satellites can sometimes get their measurements wrong, you should check out Simon Clark's video on the cold bias. Also, Scott Manley has a great video discussing satellite orbital mechanics in much more detail than we have here. And if you're really keen and would like to try your hand at analysing some of the petabytes of free satellite data, then have a look at Google Earth Engine. You'll need to do a bit of coding, but it's actually not too complicated and well worth the effort. Thanks for watching this OurEden video. Please like, comment and subscribe if you found it interesting. And as always, look after yourselves, each other, and most importantly, the planet around you. Thanks again, OurEden.